Right, let's just dive straight into this explainer and unlock the secrets of the BC488 transistor. If you've ever poked around a circuit board, you've definitely seen one of these little guys. It's a tiny, kind of unassuming component, but man, it solves some massive problems in DIY electronics. Today, we're going to completely demystify this little powerhouse so you can start using it in your own projects with absolute confidence.
So, here's our game plan for today. First, we'll meet the BC548 transistor. Second, we're going to look at exactly how it works. Third, switching versus amplifying. Fourth, building some real-world circuits. And finally, finding replacements.
All right, Section 1, meet the BC548 transistor, anatomy and specs. We're starting from the outside in, looking right at that physical TO92 package you might literally be holding in your hand right now.
Now notice the rule of 3 here. When you look at the flat side of the transistor with the legs pointing down, you've got 3 pins: collector, base, and emitter. The collector is where the main current enters. The base, well, that's your middleman, the control pin. And the emitter is where all that current leaves. But hey, here's a golden rule for your workbench. You always want to verify this exact orientation against your specific manufacturer's datasheet before you wire anything up. Package orientations can totally trick you if you're not careful.
Beyond the pins, we have to respect the physical limits of the silicon. So the BC548 is an NPN bipolar junction transistor, and it can handle a maximum collector-emitter voltage of about 30 volts. But I want you to pay special attention to the 100 milliamp continuous collector current limit. You might see some random forums online claiming it can handle 500 milliamps. Yeah, relying on that will absolutely fry your component. Always trust the datasheet's 100 milliamp limit. It clears up so much of that conflicting information.
Moving right along to Section 2, how the BC548 works, the inside story. Now that we know what it looks like and what its physical limits are, let's see how this builds into an actual working theory inside the silicon itself. Okay, if you take away just one single concept today, please make it this one. Keep this mental model anchored in your head. The BC548 is essentially a small electronic control valve. A very, very small current applied to the base acts as a valve to control a much larger current flowing between the collector and the emitter. Basically, you're using a tiny trickle of electricity to control an absolute flood of electricity.
But that valve doesn't just open up all on its own. To open it, this silicon transistor requires a forward-biased base emitter junction. Now, in plain English, that just means hitting a voltage threshold of roughly 0.6 to 0.7 volts at the base. Don't treat this number as some sort of absolute constant. It does fluctuate a bit with temperature and current, but generally speaking, 0.6 volts is the magic key that unlocks the valve.
Once you start applying that voltage, the transistor gracefully moves through 3 distinct operating regions. First up is cutoff, where the transistor is completely off, just sitting there acting like an open switch. Next, as you add a little current, it moves into the active region, where it behaves as an amplifier. And finally, if you push enough current into the base, it hits saturation. In saturation, it is fully on, behaving exactly like a closed mechanical switch.
Which brings us to Section 3, switching and amplifying signals. Let's explore these 2 very different jobs and see exactly how we harness those 3 operating regions to actually get things done.
So the BC548 has this really cool dual nature. On one hand, we have its life as a switch. In this mode, it lives in extremes. It aggressively snaps between open, that's the cutoff region, and closed, the saturation region. It's totally digital, on or off, no in between. But on the other hand, we have its life as an amplifier. Here, it gently rides that middle active region to smoothly scale up small analog signals. This makes it absolutely perfect for things like audio preamplifiers or little microphone circuits. Now, when we're hanging out in that active amplifier region, we use this really simple equation to see how the magic actually happens. The collector current equals the transistor's gain, which is represented by beta or HFE, multiplied by the base current. To put that into perspective, if your transistor has a gain of 200 and you feed just a tiny 0.1 milliamps into the base, that base current gets multiplied by the gain to create a massive 20 milliamp collector current. A tiny input creates a massive output.
All right, Section 4, real-world circuit examples. Let's pull all of this theory out of the clouds and onto the breadboard to see how it works with real components.
Let's look at a classic, driving an LED. By stepping through this simple LED driver circuit, we can watch the exact chronological chain reaction happen. Step 1, your control signal, maybe from a sensor, goes high. Step 2, this pushes a small current through a base resistor directly into the transistor. Step 3,
This current hits the base, snapping the BC548 fully on into saturation mode. And step 4, this opens the floodgates, allowing the main collector current to flow down through your LED to the emitter, lighting up the bulb. When that control signal drops, the valve closes, and boom, the LED turns off.
You can actually do the exact same thing to drive a relay, which is awesome because it lets a tiny microcontroller control heavy household appliances. But there is a massive catch here. When using the BC458 to drive a mechanical relay, you absolutely must, and I mean literally must, include a flyback diode across the relay coil. See, when a relay turns off, its magnetic field collapses and generates a huge high-voltage spike. Without a flyback diode to safely route that energy away, that spike is going to instantly destroy your fragile BC458. So don't forget it.
Okay, Section 5, finding the right replacement. Because let's face it, no matter how careful you are with those flyback diodes, eventually you're going to burn a transistor out, or you'll realize your project just needs slightly different specs. So let's talk safe substitutions.
Before we even look at entirely different part numbers, remember that even within the BC548 family, you've got to pay attention to the letters at the end of the name. The A, B, and C suffixes actually dictate wildly different gain ranges. The A version has a lower gain, roughly 110 to 220. The B is your medium ground, and the C version has a very high gain, sometimes shooting all the way up to 800. This is incredibly critical for precision amplifiers. I mean, you can't just swap an A for a C in a sensitive audio circuit and expect it to sound the same. It just won't.
But hey, what if you simply don't have a BC548 on hand at all? Well, this breakdown shows exactly what alternative you should reach for. The BC547 is generally your best overall replacement. Now, if you're building an audio circuit and need super low noise, you're going to want to grab a BC549 or a BC550. If you just need a general-purpose switch with a bit more voltage tolerance, the 2N3904 is fantastic. And if you need to drive a really heavy load that demands more switching current, the 2N2222 is going to be your absolute best friend.
I actually want to pause right here for a second because we see one specific question constantly. What is the real difference between the BC548 and the BC547? Well, comparing the two side by side, the BC547 is essentially the exact same general-purpose transistor, handling the exact same 100 milliamps of current. But it is the better choice when your circuit demands a higher collector emitter voltage rating, maxing out at roughly 45 volts compared to the BC548's 30 volts. Before you go doing any swapping, though, please memorize this checklist. Never just assume two NPN transistors are simple drop-in replacements for each other. You must meticulously check this parameter list. Verify your voltage limits, current limits, and power dissipation. But honestly, the absolute most important step is the very last one. Always verify the physical pinout. The pin configuration frequently changes between families. For example, if you try to replace a B-series transistor with a 2N series without physically twisting the legs to match the new pinout, your circuit will fail and you're probably going to let the magic smoke out of your components.
So we've covered the physical anatomy, the invisible math, the real-world breadboard circuits, and the safest ways to swap out components. With the whole mystery of this tiny electronic control valve finally solved, the only real question left is, how are you going to use this knowledge on your own workbench? Are you going to amplify a tiny microphone signal, or are you going to use it to switch on a massive relay? The possibilities are quite literally endless. Thanks so much for joining me for this explainer, and I will catch you in the next one.